So in this video, we'll look at the solutions to practice test 3 for Phys 1221. Once we've looked at the solutions, we'll look at how the questions would be marked. Okay, so this is question 1. So in this problem, we've got a small laser which has a power of 5 milliwatts. So P is equal to 5.00 times 10 to the minus 3 watts. And it's got a wavelength of 633 nanometers. So lambda is equal to 633 times 10 to the minus 9 meters. And it's focused until its diameter is 1 millimeter diameter of a sphere placed in its path. And the sphere is perfectly absorbing and has a density of 5.00 times 10 to the 3 kilograms per meter cubed and a diameter of 1 millimeter. And we're asked in part A, what is the beam intensity at the sphere's location? So in order to calculate the intensity, we're going to need to use our equation that the intensity is equal to the power over the area. So we know the power that our laser is outputting, it's 5 milliwatts, and the area that it's going over is the sphere's area, and we've got the diameter of the sphere. So the area is going to be equal to pi r squared, which is pi d on 2 squared. So we divide by pi times 1 times 10 to the minus 3 over 2 squared. And solving this on the calculator, we end up with this is equal to 6.37 times 10 to the 3 watts per meter squared. Now in part B, we're asked for the radiation pressure on the sphere. Okay, so the radiation pressure is given by I on C. And in this case, we use I on C, not 2I on C, because the photons are being absorbed by the sphere. They're not being reflected by the sphere. If the sphere was reflecting them, then the change in momentum of the photons would be double. And so we'd end up with a factor of 2 here. So we can work out what this is. We've just calculated the intensity. So we've got 6.37 times 10 to the 3. And then we divide by c, the speed of light, which is 3 times 10 to the 8. And so solving this, we end up with 2.12 times 10 to the minus 5 newtons per meter squared. And then part C asks us for the magnitude of the corresponding force. So pressure and force are related through pressure is equal to force over area. So the force is equal to the pressure times the area. And we've just calculated the pressure here, 2.12 times 10 to the minus 5. And then we discussed how to calculate the area over here, pi times the diameter squared on 2. So this is times pi times 1.00 times 10 to the minus 3 over 2 squared. And so solving this, we end up with this is equal to 1.67 times 10 to the minus 11 newtons. Okay, so let's look at how this would be marked now. Now for part A, you get a mark for realizing that the intensity is equal to the power divided by the area. So that's 1 mark. And then there's an additional mark for the correct answer. So part A is out of 2 marks. Part B, we get 1 mark for giving the correct formula relating pressure, intensity, and the speed of light. So 1 mark for that. and then again 1 mark for getting the correct final answer. For part C, again, 1 mark for realizing which equation we need to use and 1 mark for the correct final answer. We do need to have the correct units here. And so question 1 is out of 6 marks. Okay, so this is question 2. So in this question, we've got, we're at the beach and we've got water which has a refractive index of 1.33. And in the first part of the question, we're asked to calculate Brewster's angle for light reflected off water, and we may assume that the refractive index of air is 1. So in this case, we can just use our formula for Brewster's angle, which tells us that tan of Brewster's angle is equal to n, where n is the refractive index of the medium that it's being reflected off, assuming that the other medium's air, which it is in this case. And so we can say, well, Brewster's angle is going to be the inverse tan of 1.33, and solving that, we end up with 53.1 degrees as our Brewster's angle. Now in part B, it asks us use a diagram and words to explain what happens to light incident on water at Brewster's angle. So let's draw our diagram here. So we've got our incoming light ray. Now in the incoming light ray, this is unpolarized light. So we've got some which is polarized in and out of the screen, and we've got some which is polarized perpendicular to the direction it's traveling. So how we can show that is here's the light polarized perpendicular to the direction it's traveling, and here's the light polarized in and out of the screen. So we've got both polarizations existing here. And at the surface, two things happen to the light. Some of the light is reflected. So in that case, we've got the angle of incidence, which is Brewster's angle in this case, and the angle of reflection, and those are equal. And some of the light is also refracted. So it's going to bend towards the normal a little bit like this. And what's special at Brewster's angle is that this reflected and refracted rays are at 90 degrees to each other. So now what happens is when we're at Brewster's angle is that the reflected light ray here only has light polarized in and out of the screen in it. It doesn't have any of the light which is polarized perpendicular to this direction of travel. And so this means that in the refracted ray, there's a little bit less which is polarized in and out of the screen, and more of it is polarized perpendicular to the direction of travel like this. So there is a little bit like this. So this ray here is partially polarized, while this ray here is polarized. So the reflected ray is polarized in and out of the screen in this case. The refracted ray is partially polarized. The reflected and refracted rays are at 90 degrees to each other. Okay, and then in part C, we're told at a particular beach at a particular time near sundown, the horizontal component of the electric field vector is 2.3 times the vertical component. So let's write EX, the horizontal component, is equal to 2.3 EY. A standing sunbather puts on polarizing sunglasses. The glasses eliminate the horizontal field component. So glasses eliminate EX. And then in part C, we're asked what fraction of light intensity received before the glasses were put on now reach the sunbather's eyes. So because EX is eliminated, this tells us that only EY reaches the eyes. So we can work out, well, what fraction of the total electric field reaches the eyes. E total is given by the square root of EX squared plus EY squared. And then what we'll do is we'll substitute in for EX here. So this is equal to the square root of 2.3 EY squared plus EY squared, which is equal to, let's pull EY squared out the front, and because it's got a square root, that becomes EY. So we've got EY times the square root of 2.3 squared plus 1 squared. And so this is equal to 2.5 EY. So therefore the percentage of field that gets through is equal to EY over E total, which is equal to EY over 2.5 EY. And so that is equal to 2/5 or 40%. But we weren't asked for the fraction of the electric field. What we were asked for was the fraction of the light intensity. So intensity is proportional to the electric field squared. So in this case, it's 2/5 squared of the light which gets through, which is 4 on 25. So that's the fraction of the intensity that gets through. Okay, so let's see how this would be marked. For part A, 1 mark for realizing which equation we have to use and 1 mark for solving it to find Brewster's angle. It's fine if you want to give it in radians as well. If you do, it's 0.93 radians. That is also correct. Now for part B, you get 1 mark for the diagram. So, 2 marks for the diagram. So within the diagram, you need to clearly show that that's 90 degrees there, and you've got to show the incident, the reflected, and the refracted. So that's out of 2 marks. And then you also get 2 marks for pointing out the important features in words. So 1 mark for saying that the reflected ray is polarized, and 1 mark for saying that these are at 90 degrees to each other. So part B is out of 4 marks. Now part C, you get 1 mark for writing down this equation, which is just putting into an equation form the information which was given in the question. You also get a mark for calculating the total electric field, and then you get a mark for calculating the proportion of the electric field that gets through, and then another final mark for calculating the percentage of the intensity rather than the electric field that gets through. So part C is out of 4 marks. So in total, question 2 is out of 4 plus 4 plus 2, which is 10 marks. Okay, so this is question 3. So in this question, we've actually got 3 slits. So we've got, sorry, this isn't very well drawn, but this middle slit is 4 times the width of these 2 outer slits here. And then we've got a screen, which is a really long way away. And what we're considering is how bright this screen is at an angle theta with this line here. And we're told that we can denote the intensity of the radiation from the outer slit, so that's this one and this one, at the center of the screens is I naught. And in part A, we're asked what would be the relative intensity of the wave from the middle slit, which is 4 times as wide, compared to the intensity of the light coming from the outer slits. Okay, and then in part A, we're asked what would be the relative intensity of the wave from the middle slit compared to the intensity of the waves from the outer slits at the center of the screen if the plane wave is incident on all the slits. So we've got a plane wave coming in, so we've got the same intensity of light which is incident on each of these slits. Now, because this middle slit is 4 times as large as the outer slits, it's going to let 4 times as much light through. So as middle slit is 4 times as wide, it lets 4 times as much light through. And so because it's letting 4 times as much light through at the center, it's going to have 4 times as much intensity. So that'll tell us that I middle will equal 4 times IO, where IO is the intensity coming through one of these slits here. Now part B says what are the relative electric field amplitudes, and this one, once we've got the relative intensities, it's not too hard because we know that intensity is proportional to the electric field squared. So if the middle intensity is 4 times the outer intensity, the middle electric field is going to be equal to the square root of 4 times E of the outer one, and so that'll be 2 times the electric field strength at the outer, from one of these outer slits here. Now part C asks us to derive an expression for the phase difference between the 3 interfering waves at point P. So when we've got this angle theta here, this is point P up here, and we want to know, well, what's the phase difference coming from each of these different slits here. So let's draw ray 1 coming from slit 1, we've got ray 2 coming from slit 2, and we've got ray 3 coming from this third slit down here. Now in the question, we're told that this is the far field. So while these don't look parallel how I've drawn them here, because it's a far field, the screen is a long, long way away. So we can pretty much imagine these rays here as parallel. So to get the phase difference, what we're going to need to consider is, well, what's the difference in path length that these rays have traveled? So to work that out, we've got this additional distance traveled by ray 2 over ray 1. Now this angle in here is theta, which means that the angle here is also going to be theta. And so we've got this additional distance here is going to be given by d sine theta. This d is the distance between these two slits, so that's d there. And so the phase difference is going to be equal to 2 pi times the additional path length that's traveled, which is d sine theta, divided by the wavelength of the light. And then we need to do it for each of these pairs. So between ray 2 and ray 3, so this is between ray 1 and 2. Let's do ray 2 and ray 3. Again, we've got that this angle in, because this angle is theta, this angle in here is theta. So we've got 2 pi times d sine theta over lambda between ray 2 and 3. But then between ray 3 and 1, we've got these path differences we'll add together. So between ray 3 and 1, we'll have double this path difference. So we'll have 2 pi times 2d sine theta over lambda. Okay, and then in part D, it asks us hence or otherwise determine the conditions for maximum and minimum in the interference pattern. Okay, so we'll have a maximum at P when all of these are in phase with each other. So when in phase, so these will be in phase when the phase difference is equal to an integer multiple of 2 pi. So when we've got n times 2 pi is equal to 2 pi d sine theta over lambda. So these cancel out and we end up with n lambda is equal to d sine theta, where n is an integer. So we could write that this way if we want. Now it's going to be out of phase when it's traveled an extra half wavelength from this middle slit to these outer slits, because then this middle one is going to be totally out of phase. So that will happen when we have n plus a half lambda is equal to d sine theta, for n is an integer. So this is out of phase. Okay, so let's have a look at how this would be marked. For part A, we get 1 mark for realizing that it's going to let through 4 times as much light, and then 1 mark for getting this expression here. For part B, 1 mark for relating the intensity and the electric field strength, and then 1 mark for giving the expression for the electric field strength. Now for part C, we'll get 1 mark for our diagram and realizing that though they don't look at these are actually parallel, and then 1 mark for these ones here, and 1 mark for the difference between ray 1 and ray 3. And then for part D, 1 mark for the in-phase expression and 1 mark for the out-of-phase expression. So in total, we've got 2 plus 2 plus 3 plus 2, which gives us 9 marks for question 3.